Today we're going to be talking about network flows. Today we're going to be talking about network flows. So what is a network flow and why do we use it? So network flow usually concerns graphs, so nodes and connections between these nodes. And often connections between nodes represent some sort of relationship and have some sort of weight between them. So the weight between them could be the amount of resources one line can take, the connection or strength between connections, or some other association. These are used to delineate relationships between nodes. Maybe you have some sort of, let's list examples, but say you have a train system. So you say you have a train system and you want to carry resources between them, and these lines delineate the capacity at which each line can handle. It could be airports, it could be planes, or airports, let's do airports. Could be the amount of traffic that's allowed between connections. It could be just relationships, where it could be coworkers or maybe antivirus systems seeing the relationship between nodes or components in a computer to see how much a file is interacting with other files. So this is used for basically finding relationships between nodes in a graph. So what is a network flow? What do we use to represent that? We use a flow network, So a graph G, so we have some graph system, and we label this entire graph G. And each node or vertex we're going to label with V to represent the collection of all the vertices. And then we'll use E to represent the collection of all edges. So each of these edges and these points connecting them have data flowing between them. So what does that mean? So let's start out with the source node. So the source node S, where data enters the stream. So we have a source node S. So we have source node S. This is the source where data enters the stream. And then we have a sink node T, where data exits the stream. So let's say we have some sort of sink node here. So the sink node. So this would be the sink node. And then we have edges E, so UV that has a capacity in this function, putting it in the function C, UV, such that this is the maximum flow that can pass through it. So what does this mean? So say we have a node U, and say the endpoint is node V. Now, if we put this into the formula, say they had the connection between them had a capacity of 15. This would mean if we were to put this into that function, that C UV, so C U dash V would have the capacity of 15. So that when we put these through the function, it just returns with the relationship or capacity that it has. So what does this look like in an actual graph? So say, let's call this graph our G. So we start with these two nodes, the source and the sink, and let's just have two intermediary nodes. And we're going to have a directed graph. We're going to have a directed graph because the flow or the data is going from the source to the sink. So you can think of this as if we had some sort of water system where maybe we start with the sink or the enter of the pipe system where we put water into the hole. It carries throughout some pipe system going through flowing data such that we have the source and all the data is flowing, trickling all the way down to the sink. So you can think of this as pipe networks flowing water throughout systems where the source is where we put data in and the sink is where all the data ends up. So we can have intermediary nodes, say A and B, And the capacity between them, let's start out, let's use the 15, the 7, the 3, and the 2. So this means that when we enter data, say I put in maybe 20, so I put in 20 into our data, so we begin with 20 units, and say 15 of those can go through here. So out of 15, let's say 15 goes through here, and then let's say 3 goes through here. And once we reach 7, we can't pump 15 into 7 because it can only hold 7. So at most we can pump in 7, and here at most we can pump in 2. And data isn't created or destroyed, so if we pump in 15, we can't lose data, we can't lose water. So that means that we have a bottleneck here, so 7 will be our bottleneck. So here we have a bottleneck of 7. So on this path right here, the only thing that can really pass through is 7. So the only thing that can pass through here is 7 because we are bottlenecked. Again, here with this 2, we can start with 3, but in reality, this can really only handle 2 because we're bottlenecked by that 2 path. So the bottleneck here is 2. So in reality, we can only actually pass 2 in here. So we can see the amount of data that actually can reach the sink here would be 7 and 2. So that would just be 9. So the maximum amount of data that can be pumped through this system, so let's say the maximum, let's try to use a different color, the maximum amount of data that can be passed through the system, or the max flow, is equal to 9. So this is the basics of a flow network, and let's flesh this out more formally. Let's go over some technicalities. A source sink cut, or an ST cut. A partition of a flow graph into 2 sets, A and B, such that S is in A and T is in B. Namely, that B is defined as the complement to A. So let's draw our last example. So S and T, 2 intermediary nodes A and B. And let's draw our connections such that the source is flowing to the sink T. Now, if we were to draw a partition, say this one, this would be the partition A. That would mean that A would have the set S, and it would have B. Now, the set B, the big B, is going to be A and T. We can draw this another way. To say the set A was instead this partition here, so we're partitioning the graph into 2 sets. This would mean that this little a is now in the set big A. Now this is how we are going to delineate the ST cuts. If you want to deviate from this or write a different notation, just be sure to define what you are writing. But from here on out, we are going to use this as our definition of the ST cuts. So now let's talk about the capacity of a cut. We'll denote it by this function here, CAB, and AB is going to be from the ST cuts, and this is going to be the sum of the edges leaving A to B. This is such that we have nodes in A and nodes in B, particularly that U is going to V. And these are going to be the sum of all these such capacities. So let's draw our example below where we had our source and we had our sink T and our 2 intermediary nodes A and B. And we're going to complete this flow graph just real quick. And we're going to add one extra connection, which is from A to B. And we're going to give them capacities again. So let's say this is 15, 20, 30, 10, and 20. Now, we are going to create a ST cut. Say we created this ST cut here. This is going to be A, and the B is going to be everything that is not A, so that's our B. And these are going to be equal to, again, this is going to be equal to S, B, and our b here is going to be equal to a and t. It's going to be equal to a and t. Now, let's define also a cut set. So what is a cut set? So we're going to be drawing from our cut set. And what is this? These particularly are talking about edges. And what is a cut set? So we have this A here, so let's examine this A. Things or edges that are in our cut set are edges that cut across our partition. So these points are cutting across our partition. So our cut set, let's define it as, let's just do cut set here, is going to be equal to, if we have the node pairs, we're going to do S and A. We have A and B, and we have B to T. I'm just going to denote that the starting node is going to be the start and the end of the pair is going to be the end point. So these are our cut sets. But our definition here is talking about leaving A to B. So we are leaving A to B. So in this case, if we look down here, the edges that leave A to B is this node here, and this, not node, but edge, this edge here, and this bottom edge here. Now, this edge is not leaving A, it's going from B, so this outside space here, and is jumping into our partition A. So the only edges that concern us on this bottom right cut set here is going to be S to A, and is going to be B to T. So these are going to be the capacities that we're actually concerned about. Now we're going to look at their capacities, so we're going to look at 15, and we're going to look at 20, and this capacity of this cut set, is just going to be 15 plus 20, which is just going to give us 35. Now this is what a capacity of a cut is. This is what the capacity of a cut is. So let's talk about a minimum cut, or a minimum capacity cut. It is a cut CAB such that it is the minimum possible value for all cuts in the graph. So let's start out with our example again. So we have the S and T and the intermediary nodes A and B. Let's draw these connections between them. And again, the minimum capacity cut is the smallest such cut that is possibly achieved by all sums of the capacity cut. So let's draw these capacities 10, let's do 20, 20, 30, and 20. So if we were to draw this cut here, so let's start with 10 and 20. So this would be A, and the outside would be B, so everything that is not A. We would have the sum, so these are in our cut set, so that would be 10 plus 20, that is going to be equal to 30. Now if you were to draw something else, that would be, we would get 10 here and this other section here. So we do have, these are in our cut sets, but we're actually only concerned about from A going to B. So the only things we are caring about here is going to be 10 plus 20, these edges right here. This is also going to be 30. We can see that after we draw another connection here, so let's draw another ST cut, so let's draw 20 and 20, we're going to achieve here 20 plus 20 because of these cuts here. This is going to be 40. We can see from this graph the best possible cut, or the minimum or capacity cut that we can achieve is 30, and this 30, so our min cut is going to be equal to 30. And there are multiple min cuts, but a min cut is the smallest such possible capacity cut that we can achieve. This is a min cut. So now let's talk about the more formal way that we're going to define the valid graph flow. So say we had the capacities 10 or 20 here, and then 10 here, then we had 10 here and 20, and then we had a 30. So the capacity is here, so this is 20, and the amount of data flowing above it, so I'm going to denote the amount of data that's flowing through it above it, so this is going to be 10, so I'm saying there's 10 units flowing through this connection, and then 10 units flowing through this connection. So we're not worrying about the rest of the graph here. Just to simplify things, we're just going to worry about this path here. Now let's walk through this definition. So for edges UV and the graph VE, so this is going to be the graph, V vertices and E edges, we're going to denote a new function. So this is going to be FUV, and this denotes the amount of data flowing from U to V. So again, if we have U here, so this is U, and we have V here, and we had the capacity 30, then the flow is the amount of data going through it. So we're saying that, let's say 10 units was flowing through this. So then our function f would be uv, so this is uv, is going to be equal to 10. So this is just denoting how much data is flowing through an edge. And looking back at the definition, for a valid ST flow, so for a valid ST flow, f here in G has to follow the following constraints. So what are these constraints? First, we have the capacity constraint. So we're basically looking at this constraint here. All this is saying is that if we have U and V here, U and V, that so it's 0, so the amount of flow that can go through this, so if our capacity was 30, we can't have negative flow. It doesn't make sense in this definition that we're creating to have -1. That doesn't mean anything. We're only talking about filling it, as if we had a pipe system, there can't be negative flow going through it. There's water or there's not water. If there's not water, that means it's 0. So looking back at our definition, this 0 here is denoting the sort of bottom of our capacity, or the amount of flow that's allowed in. So we can only start from 0 and work our way up. So like 10, 20, and then this last constraint here, that the flow is less than or equal to the capacity UV, is saying that it doesn't make sense to have more flow than our capacity. So this is not possible because our capacity is saying we have 30 that can possibly go through this connection. So 40, that doesn't really make any sense. We can't have 40 over 30 because it can only hold 30. So in essence, that's what the capacity is talking about, that the capacity is respected, that there can't be negative capacity or flow, and there can't be flow going over the capacity. So that is the constraint. The flow conservation was talking about our bottlenecks, saying that if we have 20 units here, so a capacity of 20, that if we were to somehow pump, say, 20 through here, 20, so if we had 20 units going through, then how is it possible that we have 10 going here? Where did the other 10 go? We can't destroy data. And we can't create data. So we can't have, so to specifically look at the definition, it is V, so V and big V, so a node in all of vertices, excluding, so this dash here just means excluding S and T, so excluding S and T, so it is the sum, of, so U going to V, so these connections here, U to V, so all of these are our sets, and we're summing all of the flow, and this means that is equal to V going to W. So this means that if we have U here and W here, that the flow going from U to V is the same amount of flow going from V to U. That there's nothing being created here or anything being destroyed here, that what's going in is what's coming out. So that's what the flow of conservation is, that we can't create data, we can't destroy data, the sum of what's coming in must be the sum of what's coming out. So here we have 20 coming in, so this is this first notation here. And for some reason we have 10 here. Now this is not equal. These are not equal. So this is not a valid flow of conservation. So if we were to delete this and were to make a proper flow of conservation, we would have 10 and 10, because here we have a bottleneck, so this respects the flow of conservation. But say we had 20 going here, and we cared about the rest of the graph. Say we cared about the rest of the graph. So let's erase this. So the flow of conservation, so we have 20 going here, and 10 is only allowed here through this 10 top path. So to respect the flow of conservation, we can route another 10 units down here. We can route another 10 units down here, and this would respect the flow of conservation because the sum of these edges here is equal to this flow here. So what's coming in is what's coming out. So we're not creating anything, we're not destroying anything. The flow of 20 is being evenly distributed throughout the system. It isn't disappearing anywhere. It's all the data is present. So what comes in must come out. So let's try the rest of the graph. Let's say we had 10 units flowing in this way. So this means we have 10 units going here, and we have 10 units coming down. So this is going to be 20. So we can have 20 units going through. And we see that everything is fully saturated as much as we can go in. So we have 20 going in here and 10 going in here. And that is the same amount that we're getting at the sink. So what comes in must come out. So let's draw, what does this mean? So if we have the capacity cut here, so this was 20 and 10 because of these cuts. So that's 20 plus 10 is equal to 30. If we look at the end here, if we create a capacity cut around T, looking at these cuts here and here, that we're going to get 10 plus 20, 10 plus 20, which is equal to 30, which verifies that what we're getting in is what we are getting out. So this is the flow of conservation, and this is a valid flow graph. So this is what we mean by a valid flow graph. Let's go over two definitions. A maximum flow, or a max flow, is the maximum possible flow that can be achieved within a graph. The second term we have to be concerned with is an integral flow. This is just to say that the flows that are used are all whole numbers. This is a maximum flow, and this is what an integral flow is. Again, a maximum flow is the maximum possible flow that can be achieved in a graph. So this lemma right here is going to be one of two insights that we're going to use to prove a very important fact about finding the max flow and the min cut. So here we're going to start out with the flow value lemma. So this means for any flow, the value of that flow for any ST cut CAB, the net flow sent across the cut is equal to the flow leaving S. So that is for U and A and for V and B. So let's draw this out. So let's say we have a CAB cut right here, this A, this B, where every node inside the partition is U and every node outside of it is V. And it's saying that anything going towards V, so anything leaving the partition, is all of those summed together, subtracted by everything entering the partition. So everything entering the partition, so these two subtracted, so everything exiting and everything entering, if you take the difference between those, that is going to be equal to the flow. So let's illustrate this. So we already have this 20 up here exiting, and we have this 20 down here exiting. So that would be 20 plus 20 is equal to 40. Now we have 10 entering, so that would be 40 minus 10. This is equal to 30, which is equal to our flow. As we see here, entering our sink, we have 10 and 20. Our flow here is 30. So this holds. Let's move on to the next insight. Now, the second of the two is weak duality. So we're going to bring together our intuition and understanding about network graphs and sort of drive this point home, that for any flow f and any ST cut CAB, that the value of the flow is at most the capacity of the cut. That's to say that if we have a value flow f, that it is impossible to have the value of the flow exceed our capacity. So let's draw some capacity cut here. So let's draw this capacity cut here. And we see that we have capacity cut. This is, so we have 10 in the red and 20 in red. So our capacity here is 10 plus 20, and that is 30. So the total capacity cut here is 30. So that's to say that at most, the resources we can pass through this cut is 30 units. So it would be impossible to have a flow of 31 units. We can only at most hold 30. We can't have 40 or 50 of flow because that would exceed our bottlenecks. So this is to say that the flow at any cut should be less than or equal to, because, okay, we can have a flow of 20 because that adheres to our law of constraints and adheres to our law of conservation, that we aren't creating or destroying data and we aren't ignoring our rules of the capacities. So this is to say that weak duality is to say that the value of the flow is just less than or equal to the capacity. So in all, it's basically adhering to constraints of capacities and conservation. In all, we've been working to find this theorem, the max flow min cut theorem, that by gathering all the knowledge we've found so far, that the value of the flow, that if that is equal to our capacity cut, then that flow itself is the max flow, and that capacity cut is indeed the minimum capacity cut. As by our laws of conservation, the flow cannot get any larger than that. By contradiction, if you were to say that capacity cut weren't the min cut, then the value of the flow must be less than that capacity cut, as it must have been bottlenecked somewhere by some other smaller capacity. So now let's work through this. If I were to draw this capacity here, this is going to be, so examining 10 and 20, this is going to be 10 plus 20, which is equal to 30. Solving this before, we know that that's the minimum capacity cuts, because here in our graph, that's the smallest capacity cut we can draw, as we can also draw, let me use a different color, we could draw perhaps this capacity cut. We could draw this capacity cut, which here would be 20 and 20, so that would be 20 plus 20, which is equal to 40. And then looking at our max flow, we've solved the maximum flow for this problem already, which is if we were to draw another minimum cut here, so let's draw this minimum cut. We know the flow leaving here is 20 and 10, and we can see that the flow entering here is 20 and 10. We know that our maximum flow, I'll draw it in blue, so our maximum flow that we see, our maximum flow here is 10 plus 20, which is equal to 30. We can see here that the minimum cut is equal to our maximum flow. And that here, looking at this other cut, so this other cut we drew, I'll draw it back, that this cut is greater than our maximum flow, is greater than our maximum flow. So it was this cut right here, that 40 is greater than 30, because some other bottleneck, so our bottleneck here, stopped this capacity cut from being the minimum cut. So we can tell that if the capacity cut, so if the capacity cut is equal to the flow, so again, if the capacity cut is equal to the flow, then that must mean that the minimum capacity cut is indeed that capacity cut, and that the maximum flow is indeed that flow. That is the max flow min cut theorem. So the big question is, how do we find the maximum flow? How do we solve this graph? We could try a greedy algorithm approach, but this isn't going to work out too nicely. We can try and pick the most capacity and the most flow we can through the system, but we quickly run into errors. So say we do 20, and then we say, oh, I can put in more flow here on this 30, and we put in this 20 on this 20 over here. So following this path, following the most capacities and the most flow we can pump into the system. When we immediately go to this 10 here and try to pump in 10, we're going to run into this issue of conservation as where is this 10 going? We already have 20 flowing this direction from this zigzag up here. So how is this 10 going to fit in? We can write some more logic, maybe looking at the entire state of our graph, but as our graphs grow more and more large, it's going to be difficult to write more and more cases, so this greedy algorithm approach isn't going to work out for us in the long run. Instead, we're going to be using something called a residual graph, which is going to help us keep track of what we spent along. So we spent 20 flow this way, 20 flow that way, and help us keep track of what we haven't spent, what flow isn't used, and what flow is used. So let's talk about that. So instead of using a greedy algorithm, we're going to be using something called a residual graph. So we're going to have the original graph here. So we're going to have a U going to V, so some arbitrary nodes in the graph. And we're going to have another graph that's going to be our residual graph, which is going to mock the original graph, but keep track of what flows we have spent. The name of the game here is that our original graph is going to have the S and T sink, so the source and sink. And we're going to draw dots to symbolize that there are many connections between these points U and V, and that we don't know what they are. It's just that they are arbitrary points within the graph. So this bottom graph below is going to be G prime, and this graph above is going to be G, symbolizing the original graph. Now, what we're supposed to do in the residual graph, which is going to be reflected in the original graph, is we're going to find a point from S to T. This is also known, we're going to be performing, is called the Ford-Fulkerson, so Ford-Fulkerson algorithm. So this is what we're going to be using, and this is the general idea behind it, which uses a residual graph. So say our capacity here is 30, capacity here is 30. And the residual graph, the weights are reflecting how much flow has been used, how many units that we can use. So say we find a point from S to T on this bottom residual graph. Say we find some flow, some path, and along this path we ended up pumping 10 units of flow. So we ended up pumping 10 units of flow, so what is this going to look like? If we spent 10 going across this forward edge here, so this is going to be a forward edge as it's the original edge, then we must create a backwards edge reflecting that we just spent 10 units. So if we pumped 10 units of flow through this residual graph, we have to create a backwards edge that is that amount of units that we have spent on this edge. To reflect the new amount of units that can be used, it'll be 20. So on the residual graph, the forward edges are representing how much or how many units of flow that we can still use. The backwards edges reflect how many units we have used. And these backwards edges can be used as a path to get from S to T. So say we did take this backwards path. If we do take this backwards path, say we spent 5 going along this backwards path, finding a path to T from S, then if that's the case, we will take away 5. So if we spent 5 on the backwards path, we're spending backwards path units, and we're going to take 5 units from the backwards path and give it back to the forward edge. So instead, we're going to have 25 units now. Now, since the backwards edges in our residual graph represent the flow we have spent, the flow that we are pumping through, the original graph will reflect this, that whatever we have on our backwards edges, or whatever we have spent on the residual graph, is reflected as the flow on the original graph, So this is the basics of a residual graph. It keeps track of what we have spent and what we have left to spend, and it reflects this in the original graph of what we have spent. So let's use this on a bigger example. So let's go ahead and try an example. The top G is our original graph, and the bottom G prime is going to be our residual graph. So we're going to find a path from S to T and update our residual graph reflecting the flows in our original graph. So let's find a path. So from S, we can take this path here, from S to A, then from A to B, then from B to T. Now, what this is going to create is that we're going to spend 20 units of flow as most as we can pump through this. So we're going to create a backwards edge of 20. And then reflecting this, we're going to have our forward edge be 0. This path along here, this middle one, is going to have a backwards edge of 20 as well. We're going to have to update the forward edge, and now that's going to be 10. Then we have to create the backwards edge here again, which is going to be 20 since we spent 20. And then the new flow that we can use on this path is 0. So to reflect this in our original graph, to show this, that means we have spent 20 here, right here, since we've spent 20, so the backwards edge is 20 here. So we just have to write 20 units of flow going through. And then here we have 20 on the backwards edge, and then here we have another 20 on the backwards edge. Now, we're going to find another path from S to T. So looking back at the residual graph, we can take this bottom edge here. So we can take 10. So let's take 10 units of flow. So we're going to go back, take 10. I'm going to draw it here, and then update our flow at the bottom to be 0. Then we can take, since we're blocked here, since we can't pump any more units of flow here, since it's 0, there's no more we can do on this forward edge. We can take this backwards edge. So I'm going to spend 10 units on the backwards edge, and then I'm going to give that back to the forward edge. So that's going to be 20. Then I'm going to take this edge over here and take 10 units. It's the wrong way. I'm going to take 10 units going back. So here we're going to go 10 and reflect the forward edge. So in all, we took this zigzag path here, took this zigzag path right there. Now let's update our original graph. So now we have 10 units of flow going here. We updated the middle path. Now that's going to be 10. We have 10 units of flow here. And then we have to update this top path right over here, which is going to be 10 as well, since we have the backwards edge as 10. And we can see that, okay, let's try and find another path from S to T. And we can see that we're blocked on both of these. We can't take this path at 0. We can't take this path at 0 as well. So we're blocked here. This is known as the Ford-Fulkerson algorithm, the Ford-Fulkerson algorithm, because this finds the maximum flow. The moment we can't find a path from S to T, we have found the maximum flow. And the nodes that are reachable from S, so the nodes that are reachable from S are the min cuts. So everything that's reachable from S that is in the min cut. Here, there's nothing reachable by S. The only thing reachable by S is S, since there are backwards arrows. So let me clean this up to make it more clear. since all these are zeros, so let's just erase all the zeros here. By erasing all the zeros, we can see that we don't have any paths leading to A and B. They're all going back to S. So the only thing that reaches S is S. And this cut right here, so if we have an ST cut where this is A and this is B, the min cut here is this. So is this partition of anything reachable from S to A. So here, our min cut is this 30, and this 30 is also our max flow. So our max flow here is 30, and our min cut here is 30. Another thing is that if we flip this, and if we say everything that can touch T, so every node that can reach T is also a min cut. So in other words, if we are looking at A, anything in A, so if S can reach any other node, all the nodes that S can reach are in the partition, and this creates a min cut. And vice versa, other nodes that can reach T, so any node that can reach T, are in the B side is a min cut as well. Since nothing here reaches T, the only thing that's happening to T is that it's going outwards. The only thing that touches T here is T. And we can see that in this above graph here that this is also a min cut. And this is how we find a max flow using Ford-Fulkerson. So let's go ahead and work through an example. I encourage you to do this on your own, but you can feel free to watch along. We're going to find the maximum flow of the G graph over here. On the right, we're going to use G prime, and we're going to work through a residual graph to find the maximum flow. Here I'm just drawing out our residual graph, but again, I still encourage you to try this out on your own to figure out if you can use the Ford-Fulkerson algorithm to truly understand how this is all working. So let's go ahead and write in the flows. So this is going to be 10, 5. So these are the units that we can spend. So this is telling us how much we have left to spend. Now let's go ahead and find paths from S to T. If we can no longer find a path from S to T, we are done. So let's first take this path from S to A to B to C to T. We can see on this path our bottleneck here is the 7. So we're going to at most have 7 going through this diagram. So let's go ahead and draw back arrows. Let's go ahead and draw back arrows to get us ready. Let me draw this on the other side. So now we can only pump 7 all the way through. So let's go ahead 7, 7, 7, and 7. And let's update the flows. So this 10, since we spent 7, this is only going to have 3 left. Same with the one below. This is only going to have 3 left. On this 8 here, we're going to spend 7, so we're only going to have 1 left. And then the 7 over here on the right, we have spent all these 7 units, so we're going to have 0 left. Let's go ahead and find another path. We can take this top path right here, so S to A to T, and let's see what we get with that. The bottleneck here is this 3, so let's go ahead and use this 3. Let's draw these back arrows. There we go. So we can use 3, so take away 3, and have 0 left, and we're going to add that to our 7 up top, which is now going to become 10. Then we're going to spend our 3 over here, so our 3, and then we are going to update this 9 to a 6 since we spent 3 units from it. Now let's go ahead and find another path. So we can take this bottom path up to using the back edge and going to T. So we're using the back edge in this case, so we're going to spend back edge units. At most we can spend here is 5 since that is our bottleneck here. So we're going to go ahead and take 5 and add that to our flow and then update the forward edge of how many units we can spend. We're going to take 5 from 7, so we're going to have 2 left. Then we're going to add 5 to the forward edge, which is now going to be 8. Then we're going to go along and take 5 from this forward edge. It's going to have 1 left, add 5 to 3 on our flow, and we are going to have 5 to 3. That's going to be 8, and that'll be it. So now let's go ahead and find a new path. So we see we can't really make any more decisions here, so we must be done. Let's get rid of some of these zeros to make this a little bit more clear. So now this is our residual graph. Now, what is the min cut and what is the max flow? So to find the max flow in this, we're going to find the min cut and a ST cut. So let's draw an ST cut. What nodes can S reach? We see that we only have backwards arrows here, so the only thing that S can reach is S itself. So this is going to be the A cut in our ST cut, and this is going to be our minimum cut as well. So we can see that this is going to be 10 plus 5, so this is just going to be 15 is our max flow, and this is also a min cut. The other way to find a min cut is to look at the B partition and to see what nodes can reach T. We can see A can reach T, B can reach T through that backwards edge, and C can reach T through backwards edges and this last forward edge. So our partition on the B side is going to be this large thing here. So this is going to be the B partition, A, B, C, and T. And if you can see, that also forms this capacity cut here where we have this 10 plus 5. So that's how we're going to get the min cuts. And that's how you solve this network flow problem. So we are now going to switch gears to work our way into finding relationships between nodes. Can we find pairings between two sets of nodes, or can we find relationships within a graph? In order to work up to this, we need to establish some terminology. So we're going to now work on a bipartite graph, and this is the definition. So given a graph of G with V vertices and E edges, such that V is defined as the union of two sets L and R. So we have down here, we have L, which is comprised of 1 through 5. We have R, which is comprised of 1 prime through 5 prime. So we have these two sets right here. And where E connects L to R, so we have these connections going from L to R or R to L, a cut which separates V into two sets L and R is called a bipartition. So here we've made it pretty easy to create a bipartition since we've labeled these L and R. So we can easily just create this line in the center and create a bipartition. We're going to be separating them into two sets. And this is to say that L and R could just be part of the whole set of V, but we can make some partition that separates them into two sets, which we can find connections between. This is called a bipartition, and this is a bipartite graph. So now say we wanted to find the maximum possible pairs that we can find in this graph that doesn't reuse any of the center edges, so unique matches between L and R. So we can try to do, maybe 1 to 2. Now we can't really find a pair here because we'd be reusing, so that wouldn't be a unique pair. So we can only do maybe 3 to 3 and 4 to 5. We could try another one. We could do 1 to 1, 2 to 2, 3 to 3, and maybe 5 to 5, but we can't do 4 to 2 because that would be two people matching with the same node, so we can't really do that. So this is the most we can achieve. A way to solve this, actually, a smart way to solve it is that we can actually write a source and a sink node, and you can hook them up to one side. So we can hook this S up to this side over here, and then we can hook the R set to the sink. These are going to be flowing from left to right. So we're going to have this flow from left to right, this flow from left to right. And we can think about this as if we can find the maximum flow here, we can find the maximum amount of connections between all these nodes in order to get to the sink. So we're going to fill up our graph. And you can think of this as like a bunch of pipes, and if we flow this through the system, the water as it travels is going to reveal all of the relationships as it tries to find the maximum flow, the maximum amount of connections that it can make. So how do we set up the capacities? Well, to do this, we can actually just set all the capacities to 1. So if we can set all the capacities to these edges to 1, and that will reveal that. So when we use this edge up here, we can no longer take this path. So we're using up this one slot. And once this happens, it can only choose one of its two options. So say it makes this top option here, so we can no longer use that path, and the capacities over here are 1, so it's going to take this one path over here. And you can see that, okay, again, if we go down this one path right here, of course we're going to have backwards edges depending on the algorithm that you use. You can use any maximum flow algorithms. The Ford-Fulkerson algorithm that we used is not the only maximum flow algorithm, but it's the one that we chose for today. So we can take this 2, then the only option that 2 has is this 2 right here, and then we can take, and that just goes all the way to the sink. We can take this 3, it has 3 options to take for the 1. So why can't it take this top path right here? Well, the capacity is already full, and if we were to take this path, there's only a backwards edge leading, since we only have one edge here, and there's a backwards edge leading here, so there's no way for us to actually get to t since there's a backwards edge. Remember, if we're using Ford-Fulkerson, there is some sort of backwards edge stopping us when the flow is already filled up. So we can't use prime 1 or prime 2, so we're forced to take this path right here. We could take this 4 path over here. There's nothing really stopping us, but say we took this 3 prime here, then we're going to keep going ahead and trying to figure this out. We're going to try to take this 4 path, and we could take this 4 path all the way down to 5, going all the way back up. And then once we reach this 5 here, we're going to see that we really can't go anywhere else. We can't find another path from S to T, so we're done. So this is a way to find a maximum stable pairings between nodes, is hooking up a source node to one partition, and then hooking up the sink node to the other partition, and seeing how data flows from one partition to the next to reveal the relationships in finding a maximum flow. Let's go over some more terminology. Let's go over edge-disjoint paths. So edge-disjoint paths. This is given a graph G of V vertices and E edges, 2 paths P1 and P2 are edge-disjoint if they share no edges in common, though they may share nodes. So if we look at P1 here on the bottom, which is this red path, so S to 2 to 3 to 6 to 5 to T, and then this blue path, we can see that this blue path and this red path, they have unique edges that they take on their path to T. Right here, it has unique edges on its path to T, so they are edge disjoint. They may share, maybe intermediary nodes, so they may share nodes to get to that end result, but the edges that they choose to get to T are unique. They are unique. So this is edge-disjoint path, where there's a path that takes a unique set of edges to get to T from other paths. So that is a edge-disjoint path. So our next question is, given any arbitrary graph, how do we find the maximum number of disjoint edge pairs? We can do this. We're going to use this graph from before as a guide, but to do this, we can essentially put a capacity of 1 on all of our edges, and then run a max flow algorithm. So say we're to run Ford-Fulkerson. So if we run Ford-Fulkerson and we take this path up here, since all the capacities are 1, we are going to essentially not be able to take that path again. So we can't take that path again, since all of these are going to be all back arrows. So imagine we have multiple back arrows here. So back arrow, back arrow, back arrow. So it's going to stop us from taking that path again. And we take this red path, So we're going along and taking this red path to find the maximum flow, and we're going to get another set of back arrows. So we're not going to be able to take this path again, we're not going to be able to take this path again, and so forth. Then we're going to try to take this bottom path here. So we're going to try to take this bottom path, and we can see that we're going to get blockaded, and we can only really reach these edges here. Because we're going to go down, we can go to this back edge, go to this back edge, or we can go up again, go to this back edge, go straight back to S. So the only nodes that we can reach from S here is going to be these 3 nodes that we've circled in the green, and the arrows facing outward. So the arrows facing outward, so we have 1 here and then 1 over here. It's going to be 1 plus 1, and that's 2, and that we find that the max number of DE, let's call it disjoint edge pairs, is equal to the maximum flow, because those are all the unique paths that we can take from S to T. So in this case, the number of disjoint edge paths is equal to the maximum flow. So now we have some intuition behind how maximum flow can give us relationships in data. So let's start with a real-world problem. Say we have farmers. So say we have farmers, and we're going to define this as Fn, so there's n farmers. And say we have C communities, so we have communities here. I'm just going to say com, and those are some n C communities. And we want to know, so we have farmers, so here we have farm 1, farm 2, farm 3, and they all provide resources. So this provides resource 7, 8 resources, 6 resources. And we want to know, is this enough? So with the routes we have on hand, so these connections between, we could think of these as roads, as resource routes towards these communities. Do we have enough resources from these farmers to satisfy these communities? Do we have enough resources to satisfy them? So we're going to go ahead and work through this problem. So how do we deal with multiple sources and multiple sinks? I'd like to point out the relationship that's happening here. So we have a supply and demand relationship, where the farmers are supplying and the communities are demanding. So we can see that we're inputting sources to sync to our demands. So we can see that we can use something called a super source that acts as a catalyst for all other sources. So we can use this super source to say, okay, we're putting in these resources. So we can have a capacity of 7, a capacity of 8, and a capacity of 6 to say, this is what we can flow to these networks. And our sinks, so we're putting 7, 8, 6 into the network. What are we taking out of the network? Where is it sinking to? Where is it being put towards? We can put these and have a super sink where we can take all the demands and put them into one sink. So we're going to have 10, and we're going to have 11 here. Now, in order to solve this problem, we can run a Ford-Fulkerson or a max flow algorithm to solve this problem. And how do we know that it's satisfied? We can tell that it's satisfied when these last entries here, are fully saturated. So if we run Ford-Fulkerson or some max flow algorithm, if by the end we end up with 10 and 11 going in, then we know we are fully satisfied. It's possible that there could be more, resources that can go into these, but if they bottleneck fully saturated, that's how we know we have at least the amount of resources that we need in order to supply or support these communities. And that's how you solve multiple sources and multiple sinks. It's about finding that supply and demand relationship and hooking up your super source to the suppliers and your super sink to the demanders. before moving on, if you are interested in the final result, here it is. We can see that we are inputting 7, 8, and 6. This is going to work out to 21 inputs of units. And we can see that here, the capacities, we really want to look at the capacities here. So the capacities added up are 21. And we can see that they are fully saturated. So we're putting in 21 units of flow, and the sink is getting 21 units of flow. So the capacity of 21 is fully satisfied. So we can at least supply these communities with what they need. Let's work on our last example. We're going to call this the doctor's office. And let's say you're a manager and you have n doctors. So you have n doctors. And you have D days. So you have D days. And on these D days, every day is going to be busier or less busy. And sort of the general hot spots for days. So you say for day 1, you have a partial list ready. So you have for day 1, you need at least 3 people to be on the job. For day 2, you need at least 4 people, and day M and so on. So day M is going to need X people. So you know that you're going to need for each day a certain amount of people that you need. And the n doctors, every n doctor, so let's look at n1. So the first doctor has a list of days that they can complete. So Doctor 1 says, I can do day 1, I can do day 2, and so on. And then for the let's say Doctor, I don't know Y, for Doctor Y, they have some list of days that they can complete. And the problem statement is saying, okay, with the doctors we have, so if we are supplied with n doctors and their lists, and we have D days and every day has a requirement, how can we solve this problem? How can we know that we have enough doctors to fulfill all D days? Okay, so how do we solve this problem? We know we have n doctors and D days. We can use network flows to solve this problem because we can see a supply and demand relationship. Can you go ahead and try to figure out what the supply and demand is? Okay, so we have n doctors being the suppliers and D days being the demanders. So how can we craft a bipartite graph or a network flow graph that depicts this, that we can solve with the maximum flow algorithm? Okay, so I'm going to go ahead now and try to solve this. So we're going to have n doctors. I encourage you to do this by yourself, but here we go. So, and we have n doctors, so we have these n doctors over here. These are our n doctors, and every doctor has a list of days. Then we have our D days, so let's say we have these days over here, we have 4 days over here, and these 4 days, let's say we need 2 people, 3 people, let's say we need 4 people, and then we need 2 people again. So with these days, so we know these are going to be our days, so how do we encode, let's say this is Dr. 1, 2, 3, 4, and 5, so how do we encode the doctor's lists? How do we encode that? Well, let's say Dr. 1 can work days 2, so let's call this day 1, 2, 3, and 4. And inside the circle is the demand for that day. So we can draw, say Dr. 1 can do day 1 and day 3. So Dr. 1 can do day 1 and day 3. Dr. 2 is very busy and can only do, say, day 2. And then Dr. 3 says their schedule, I can do day 1, and I can do day 2. And then the Dr. 4 says, okay, I can do day 3, this day 2, and I can do the last day. Dr. 5 says I can do the last day, and I can do the 3rd day, and I can do the 3rd and the 1st. So Dr. 5 can do everything. Now we have multiple suppliers and multiple demanders, so we're going to then use a super source and a super sink. Now, can you guess what we're going to put for our super source? And what we're going to put for these middle capacities, and what we're going to be putting for these sink capacities. Let's start with the middle. So every day, or every day that a doctor can take, is just one day, is one connection. So the capacity should be 1 so that we don't overcount. So all these middle capacities here are just going to be 1. And the capacities over here that we need are going to reflect the day's demands. So how much flow are we letting into these gates? So we're going to see that we're going to put 2 here. We're going to reflect the need for that day. So we're going to have capacity 4, capacity 3, and capacity 2. And we're going to look to see by the end, do we have a flow that satisfies 2 plus 3 plus 4 plus 2. So we're going to get 5, we're going to get 5, and we're going to get 5 and 4, 9, 9 and 2, 11. So can we find something that satisfies 11? Are we going to have a flow of 11? So what should we put here? What should we put here for the source, the super source? We have multiple, we could maybe put 2, so we know Dr. 1 has 2, and we know Dr. 2 has one day, so we could put the actual capacities there. But say we don't know the capacity off the top of our head, or say we just want to be lazy. It is possible to put infinity here, so we can put infinity for the source. And you may ask, why can we do this? It's because we're still bottlenecked. We're still bottlenecked by this 1 here. So if we have this 1, we take this path, there's nothing really infinity can do. We can have a back arrow of 2, and we're going to have back arrows of this 1 and back arrows of this 1. Even though we have infinity here, we still can't do anything, so it's not going to overcount any connections because we're going to be bottlenecked by the schedule that doctor has for that day. So that's why we can put infinity at the beginning, but you can also alternatively just put the capacity to be 2 because we know we only have 2 days that we can work with. So it's up to the programmer in that case what to put there. And if we run a max flow algorithm on this, we will end up getting the correct answer. If you want to work through this or find a smaller example and work through this, you'll find that if all of these are saturated, you have a satisfied list. So what is the runtime for Ford-Fulkerson? So we're going to work through this, and we're going to look at the algorithm, think it through manually in our heads, and work through what possibly could be the runtime for this. So we're going to have S and T, and between S and T we're going to have intermediary nodes, so some nodes between these, and we're just going to find the maximum flow of this. In order to do this, we have some residual graph to help aid us in finding what have we spent and what we have yet to spend. So we're going to look at this, and we're going to have the G graph and G prime, so the original and the residual graph, and work our way through and say, can I find a path from S to T? If I can no longer find a path from S to T, then we have found the maximum flow, and the algorithm is done. So let's work through some pseudocode. So we're going to define, let's say FF for Ford-Fulkerson, and Ford-Fulkerson is going to take in a G graph. So we're going to take in G graph. And the first thing we do is we're going to create our residual graph. So let's say R gets create. So we're going to create the residual graph. So create res given our G. And we're basically just creating a copy of our graph here, but we're going to use for different purposes. So at most, since we're just copying, we're just going to do n plus m for n nodes and m connections. And then in our algorithm, we said find a path from S to T. So while there's a path from S to T, so that's going to be our first while loop. So we're going to say while there is, let's create a function here, and this function is going to be find path. So find path, we're going to give that to, say, P, and we know while we're finding that path, we have some sort of bottleneck. So let's give that to B. So while we have a path from S to T, so that's going to be B or P, and then we have a bottleneck P, we're going to update the flows. So update the flows, we're going to create back edges, forward edges, and we're going to update the flow in the original graph. So to do that, let's write a function called update. So we're going to do update, and we're going to update using the p and the b. So what are the runtimes for these? So if we're going to find a path, from in a graph structure, we could use BFS or DFS. They both do n plus m. So in all, this outer for loop is going to run n plus m. So we could be using BFS. And since it's n plus m, we know that m is at most, so m is less than or equal to n squared, which the amount of connections could be a full adjacency tree or full connections where every node is connected to every other node. So in all, we're actually going to say that this outer for loop is running m times. And then we're going to run this update function where we're going to update the flows with the path p and the bottleneck b. But how large could p possibly be in the worst case? So we know p is some path from s to t. So it starts with s and ends with t. And we could have some intermediary nodes in here like a and b and so on. So what it's going to look like running the algorithm, we're going to say calculate the flow from s to a, and then from a to b, from b to so on, and then from so on to t. So this could at most be n, all the nodes in the graph. So we could at most use all the nodes in the graph. So we know we're going to have at most n runtime. So we're going to go down. So this is going to be most at n. And updating that, as we're stepping through, this can be O of 1 as we update the backwards edges. So it's just going to take O of n for the update, because as we go through the residual graph, we can just update everything we need at the same time in the original graph. So it's just going to be O of n. So we see that right now we have a big O of nm since we have this nested for loop. But there's one thing we aren't considering. So let me write this all the way up at the top here. We have n and m. Let's say in the unfortunate circumstance, so in the worst case, we have all these nodes, and all these nodes have connections between them, so all these nodes have connections between them, but for some reason, our capacities, so say we had x, y, and z capacities, for some reason, they only keep incrementing up by one of their flow. So we have these capacities again, so we have, say, capacity x, and for some reason, every iteration of this algorithm, it keeps increasing by one, and by one, and then so on. How is this going to stop? When is this going to stop? If for the bizarre reason everything keeps incrementing by one, what is going to break this? Well, the only thing that's going to break this is the largest capacity. So that's why we do it m times, but the amount of times this runs is our largest capacity. So I'm going to put big C up at the top. So in reality, what's going to stop this, why our runtime is nmc, where n is the nodes, m is the connections, and c is the largest capacity in our algorithm. It's the largest capacity in our algorithm. That's going to make our algorithm run, because if in the worst case it keeps incrementing up by one for all the flows, this is going to break once we hit the largest capacity. Again, that is big O of nmc, where c is the largest capacity. And that is the end of this video. If you enjoyed it, don't forget to like and subscribe. If you are looking for code implementations, in the description below, we have an open source repository of Python code and more examples to work through. These videos are more up to date, so if you find any discrepancies, feel free to add a pull request or issue a GitHub issue. And with that, thank you.